and welcome back to Daily Planet. I'm Zaya Tong.
I'm Jang. Still lots of cool science to fit into the second half of the show today. From how time passes if you're an insect, that's on Zyology,
to why scientists are drilling 4 kilometers into the San Andreas Fault in California.
We're also going to find out why the internet is indeed the future, even for you people watching this show on television. That's just ahead on Planet U. But first, scientists know a lot about how animals move through the air or through water, but what about those animals that move through dirt? There's plenty of those. Scientists only now are beginning to understand exactly how they do it.
That's what's happening at a lab in Atlanta, Georgia, where they're studying a little creature that's very good at moving through sand. But it does it all without digging. So how does it do it? You're about to find out.
At a biomechanics lab at Georgia Tech, students study creepy crawlies and robots as they walk and run to learn the physics behind what happens when feet hit granular material like sand.
Oh, buddy. Oh.
Now lab head Dan Goldman has turned his attention to an elusive creature.
Got him.
That swims through sand.
This is a sandfish lizard, a small lizard that lives in the deserts of North Africa and runs using its limbs on the surface of sand to escape the heat or escape predators. It dives into the sand within about a half a second.
Up till now, it's been a mystery how this animal can move through sand so quickly. So Dan and his students are using imaging technology to learn its secrets.
So initially, we wanted to understand what the animal did, so we filmed it with high-speed video. And once within the medium, we realized that the visible light high-speed cameras were insufficient to give us some insight into what was going on. So we obtained high-speed X-ray imaging equipment.
Using X-ray equipment means the researchers must suit up with lead-lined gear to protect themselves from radiation. To make high-speed X-ray movies, they built an apparatus over the imaging system. Air is blown through the sand to erase any old footprints and to make sure it's loosely packed. A skittish sandfish is placed in a holding chamber. The researchers move behind a protective shield, open a gate, and trigger the high-speed camera. What Dan and his students see surprises them.
And the next step after that was to scratch our heads in amazement when we realized that the animal was no longer using its limbs to move within the sand, but was instead propelling itself forward using large amplitude undulations of its body, a wave traveling from its snout, its head, to its tail.
Somehow, the sandfish is using that wave traveling down its body to propel itself through sand. How does that wave overcome the drag force of the sand? The next step is to see if these little guys can swim through tightly packed sand. Air is pulsed through it to compact it. The camera is triggered. The sandfish moves just as fast through dense sand. How can that be? Those big snake-like wave motions are somehow the key. Dan's student Yang Ding attacks the problem by thinking small. To a tiny nematode worm, water is viscous, so it too uses big snake-like motions to swim through it. Scientists dissected the physics behind those motions by dividing bodies into imaginary segments and calculating the drag acting on each segment. Ding does the same thing with the sandfish, but some real-world numbers are missing.
So another student in the group, Chen Li, made a kind of artificial sandfish segment, which was basically a little cylinder, and dragged it through a granular medium of the same compactions that we used in the animal experiment.
That little cylinder represents a segment of a sandfish. As it moves through the sand, the drag force is measured.
Then we needed the theta.
Yang Ding plugs in the new information, and it works. The equations prove these big snake-like motions are key. Evolution has given the sandfish a wave pattern that's great at overcoming the drag of the sand. To speed up through dense sand, it just increases the frequency of the wave.
The rough rule is that the animal does the exact same thing regardless of the compaction of the material. And that was the big surprise.
Dan and his students write a scientific paper on their discovery. It's published in the prestigious journal Science. But there's still a lot to learn from the sandfish. Now Dan's students are building computer models to look at the behavior of individual particles of sand as the sandfish squirms by.
The Computer modeling allows us to simulate the sandfish more realistically. The nice feature of the numerical simulation is that it allows us to vary parameters in the sandfish. We can vary how large an amplitude it uses, how much friction there is between its body and the grains.
Another one of Dan's students, Ron Maladin, is experimenting with a robot sandfish.
It will give us insight into how properties of the animal, like its skin friction, its body shape, will affect locomotion, and this can lead to the development of better subsurface locomotor devices.
The idea is to help engineers design a robot that could rescue people who are buried alive.
We would like to hope that some of the principles we've discovered in how the animals move can inspire the next generation of devices which can actually move within complicated shifting material.
But until then, when it comes to swimming through sand, this little guy reigns supreme.